Welcome back to Arts Learning. In this video, we'll go over everything regarding the electric field, which covers adding vectors in the electric fields, how to compute the electric fields themselves, as well as how to draw electric fields. And the drawing will be the most important part, so stay tuned for that. That will come towards the end of the video. So first, let's introduce ourselves to the electric field. So the electric field, right? It's a phenomenon that states that every charge around it emits a field, okay? Which means it has, it doesn't have these, but it's represented as multiple lines. And depending on where you are on this line, so suppose the charge was over here, you'd feel a force pointing that way alongside this line. And if you have more magnitude, you'd have more lines, okay? If you have less, similarly, you'll have less. So electric charge is very similar to a magnetic field, right? You know how magnetic fields look like this, right? Very similar to that. So for magnetic fields, you understand that if you place a magnet inside a magnetic field, it's going to be attracted to that magnet. Similarly, if you place a charge inside another charge's electric field, it will either attract or repel with that charge, and it'll interact with that charge. Okay? So now, let's take a look at what it's quantized, okay? We'll go over the more drawing mechanics later in the third part of this video, but for now, let's look at what the field actually is. How do you quantify it? So the field is defined by the formula, the energy of the electric field. So not the energy, just the electric field is K times Q over R squared. And K here, we already know what K is, but doesn't this look very similar to the Coulomb's law, right? Which was KQ1, Q2 over R squared. So that makes sense because over here it's saying, basically it's saying that if you have a charge, right? The charge will have a field. And depending on where you place another charge, so if you place another charge over here, then R would be the distance from this charge to this charge, right? Energy, so the field is quantized by that. It's the magnitude of the field at that point, okay? How strongly is the field at the point where this proton or electron is placed, okay? So that's what it is. It's the strength of the field at a certain point. Now, let's dig deeper into that idea. So we know that energy is equal to K times Q over R squared, right? If K times Q1 times Q2 over R squared gives a Newton, then this is just missing 1 Coulomb, right? So it should be in units of Newton per Coulomb. And then if you multiply it, if you had another Coulomb, then you could multiply that and get a Newton. But since you don't have that, you'll have to stick with the Newtons per Coulomb, okay? Now let's look at, so I'll go over these in more depth in the drawing conventions. We're not going to go over drawing fields, but let's just look at what they look like for now, okay? An electron has arrows pointing inward, okay? All the arrows in an electron point inward towards it, like you can see here. The arrows on a proton point outwards. So that's just how we define it, because these two have different tendencies, right? That's just how we define it, just our convention. But it doesn't need to be that way. It's just our convention, okay? Protons point outward, okay? Arrows point outward. Think of it as emitting the force. It's not technically correct, but think of it as it's emitting the force. And electrons, think of them as pulling stuff in because they're electricity, right? Think of them as pulling stuff in. Think of them as the main they're attracting stuff. They're the ones moving electricity and all that. So a charge Q in the field always feels F is equal to Q times E, which makes sense, right? At a point, so energy is equal to KQ over R squared. The force that, if you put another Q in the field, it makes sense because that's just K times Q over R squared. So Q times E is just this, right? So electric field is different from the force emitted on the electric field. Force is just Coulomb's law. So the field exists with or without a test charge. So even if you don't have a magnet, the magnetic field still exists, right? We still know it exists. Very similar with the electric fields. We still know the electric field exists despite not having a charge to measure that reaction with. And denser lines mean a stronger field. So basically, if I put a charge over here, that charge would feel a lesser force than a charge put over here, okay? Because the lines over here are denser. They're closer to each other, right? The more dense a line is, right, lines are to each other, the stronger the force will be. The stronger the field as well. Okay, so lines look like this. So these are all protons. Would at this point over here would be more stronger than lines that look like that, right? The denser the field is, the stronger the denser the arrows are, sorry, the stronger the field and the stronger the force subsequently. Right, so let's take a look at this. We need to find E at 0.3 meters from a positive 4 microcoulomb charge. Microcoulomb is, micro is 10 to the negative 6, right? So this is 4 times 10 to the negative 6 coulombs. And if you need to find E, that's just K, 8.99 times 10 to the 9, times Q, 4 times 10 to the negative 6, times, well, that's it, right? An electric field doesn't need two charges. It's just the force emitted, not the force, I don't want to say force, but think of it as the strength emitted by one charge at a certain point. Okay, and that over 0.3 squared. Because it's over R squared, right? So K times Q over R squared, which would give you 4 times 10 to the 5 Newton per coulomb. And it's going to be directed away, right? Because protons are just like that. They direct forces away from them. Okay? They push outward, think of it that way. And electrons pull inward because they're more like the main character, sort of. They have more energy, right? They're electricity. It's the flow of electrons. So you can think of them as pulling stuff inward. Okay, so now let's try some practice. The field 0.5 meters from a charge is 3.6 times 10 to the 4 Newton per coulomb, pointing inward towards the charge. Find the charge, sign, and magnitude. So let's just write a formula here. Field strength is K times big Q over R squared, right? So we know that 3.6 times 10 to the 4 Newton per coulomb, because that's what we're doing, right? That's the strength of the electric field at a certain point. Is 8.99 times 10 to the 9 times Q, which is, we don't know. We're trying to find that out. And then that over R squared. So R squared is 0.5 squared. And so see what this gives you. So this is about, before you calculate anything, right? We can do Q. So you could calculate here and then you could divide this by Q, but I don't want, we can simplify further, right? 3.6 times 10 to the 4 times 0.25. All of that over 8.99 times 10 to the 9. So let's plug that in and see what we get. So 3.6 times 10 to the 4 times 0.25 divided by 8.99 times 10 to the 9. And I'm not going to use units here because it's going to get messy, but my final answer, I will. Okay? So this is about Q is equal to 1.35 times 10, or sorry, well, that was looking at something else. I was looking at my previous answer for something else. So Q here is 1 times 10 to the negative 6 coulombs. Okay. And what's the sign of the charge? So is it positive or negative? If the arrows are pointing inward, what does that tell you? It's a electron, negative charge, right? So it would be Q is equal to negative 1 times 10 to the 6 coulombs. Or 10 to the negative 6, sorry. Okay. So how far from a positive 5 microcoulomb charge is the field exactly 2 times 10 to the 5 Newton per coulomb? So same formula here. Energy is equal to K times big Q over R squared. 2 times 10 to the 5 is equal to 8.99 times 10 to the 9 times Q, which we know, 5 microcoulombs, times 10 to the negative 6, over R squared, which we are trying to find out, right? So R squared is just, let me erase this stuff here so I have more space. R squared is 8.99 times 10 to the 9 times 5 times 10 to the negative 6 over 2 times 10 to the 5. Okay, so this is 8.99 times 5 times 10 to the negative 2 over 2, right? So this would be 3. So then 3 minus 5 would give you the 2, negative 2. So let's see what this gives us. 8.99 times 5 times 0.01 divided by 2. It should give you approximately 0.22475. That's R squared, right? So R is just the square root of that. And since we use SI units, right? Because we converted from microcoulombs to coulombs, and likewise, our answer is similarly going to be in SI units, so meters. So square root 0.22475. Okay. And you should get approximately 0.474 meters. There you go. Right, so now let's look at adding fields together. So we have 2 charges, 2 fields. The net field is their vector sum, not their scalar sum, okay? Because we're taking into account direction here as well. So similarly, you know superposition, right? We learned this back in unit 1 or 2, but a long time back. Same thing. We move vectors to, so we could move this E2 here to E1, and then we could construct E net from that. So just same thing we already know, right? But what we're going to look at is how we can superpose with net fields, okay, with electric fields. So let's take a look at that. So you have two charges, 3 microcoulombs at 0, 0, okay? And then negative 3 microcoulombs at 0 0.4, 0. And we need to find E at the midpoint 2 or 0 0.2, 0. All right? Energy 1, or I want to say the magnitude of the field, the strength of the field, 1, which is this one, is K times 3 times 10 to the negative 6, and then KQ over R squared. So what's the distance from the midpoint? The distance from the midpoint is 0 0.2, right? It's from here to here, 0 0.2, because here is 0 0.2, here is 0. Okay? And then energy 2, similarly, K times 3 times 10 to the negative 6. Right here, we're just looking for the magnitude, not the sign. And then that over 0 0.2 squared again, because it's from 0 0.2 to 0 0.4. Okay? And then for this energy, you should get about 6.74 times 10 to the 5. For this one, we get the same answer because you plugged in basically the same stuff. And what's happening here is, if you remember the direction of the proton, right? It pushes outward. Think of it that way. Right? And it's going to push this charge. So that's technically not what's happening here, but it's easier to memorize. So think of that as pushing it outward. This charge is pushed this way by E1, okay? And then this electron here, what do the forces on an electron look like? I mean, the field of an electron. They all point inward, right? So the electron is going to pull this charge here, or I mean, not the charge. It just, at that point, it's going to have field lines pointing this way, okay? So the electron has these, right, pointing horizontally right, and the proton also has these pointing horizontally right. So at that point, they're going to add, and it's going to become 6.74 times 10 to the 5, the entire thing times 2, because it's the same thing, okay? And then you can get 1.35 times 10 to the 6, and that's your Newton per Coulomb. That's Newton per Coulomb, and that's your energy. Or I don't want to keep saying energy, just your magnitude of your field at that point. Okay? So let's look at practice at 2p actually. We have 2 microcoulomb at 0, 0, okay? Positive 2 here. So let me actually draw that out before I do anything. 2 microcoulomb at 0, 0. Actually, if you can say, consider this as starting from the origin. And then we have 2 microcoulomb at 0, 0 0.3. So, yeah, we can just, actually, I shouldn't have probably drawn it over there, but over here, we can consider this to be 0, 0, this to be 0, 0 0.3. Okay. We need to find the net field at 0 0.4, 0. So that's a ways off. That's like, so 0 here, so it's about here, okay? Here. How are we going to do that? Well, first, same formula, right? For this charge, it's going to be a bit easy. It's going to be just energy, or magnitude of the field there, is K, 8.99 times 10 to the 9, right? Times big Q, which is, at that point, 2 microcoulombs, 2 times 10 to the negative 6. All of that over R squared. So how far is this here? It's 0 0.4, right? So this distance is 0 0.4. 0 0.4 squared. So what that's going to give you looks like, let's see, let's compute it here. Before we compute it, we can simplify a bit. 8.99 times 2 over 0 0.16 times 10 to the 3, just 10 to the 3. Okay. So from there, you can see 8.99 times 2 times 1,000 divided by 0.16. So 0.16. So it's a lot of coulombs, okay? It's 112,375 coulombs. So 112,000. And from there, next step is to find out the force that this is pushing here. Okay? It's also going to have a field at that point, right? But that we don't know the radius of. So here we know this length is 0.3 because it goes 0.3 above from this charge. So we know this point here is 0.4 here, away from 2 microcoulomb charge over here. So this has to be 0.5. Pythagorean triple, right? 3, 4, 5. Divide the entire thing by 10, 0.3, 0.4, 0.5. And then strength of the magnetic field, 8.99 times 10 to the 9, times 2 times 10 to the negative 6. But over here it's 0.5 squared. So similar, 8.99 times 2 times 10 to the 3, but divided by 0.25. So let's see what this gets us here. 8.99 times 2 times 1000 divided by 0.25. So this is about 71,920 coulombs. Okay? So if I was to just show you what this looks like, actually let me draw this over here. The midpoint is over here, right? And since these are both protons, they're both going to have outward arrows. So this one's going to have an outward arrow here, the top one. This one is also going to have an outward arrow. Okay? And that means that they're both pushing rightward, which is a good sign. But one of them is also pushing downward. So the net energy, so the net field strength, right? It's going to be a bit different because we have 2 horizontal components and 1 vertical. So we have to add these components. And let's go ahead and do that. So 0.5. And we know this is 71,920 coulombs, right? How do we find the components of this? Well, we can just take the sign. So sine and cosine here. So this is theta, we can assume. 71,920 times sine of theta for its y component, right? For y component. Sine of theta, if you look at theta as over here, that's opposite over hypotenuse, right? So that's times 0.3 over 0.5. Let's see what that is. Okay, that is 71,920 divided by 0.5 times 0.3. So that's 43,152 Newton per coulomb. Okay, and same thing, but this time we're going to do it for the y. So I'm just going to write this as, this time for the x. So energy in the x here is same 71,920, but this time times cosine of theta, right? Cosine of theta is adjacent over hypotenuse. And if you look at this angle here, right? Adjacent is 0.4 and hypotenuse is 0.5. So 71,920 times 0.4 over 0.5. And so that should be about 57,536. Okay, so 57,536. And then we can obviously add these together. The EX plus this EX, so 56,536 plus 112,375, right? That's your x here, and your y is the negative of this because you're being pushed in the downward direction. All right. And once you do that, you can get, so 57,536 plus 112,375. That's about 169,911. Okay. And then negative 50, 43,152. If you want to find the net force here, you can just take the square root of the net field strength. You can take the square root of the field in the x and the y. Both of these are squared, right? And you should get, it's 169,911 squared plus 43,152 squared. And I don't need to put the negative because it doesn't matter, right? Once I square the negative, it will just give me the same answer. And you should get 175,305 newtons per coulomb. And there you go, finally, right? A lot of steps, but here we go. And they didn't ask me for the direction, but if they did, we could just do arctangent of field y over field x, but they didn't ask me for that, right? So I'm not going to do extra stuff here. So I can just write down 175,305 and erase all this mess. Okay. And 175,305 Newton per Coulomb. Now let's look at the fourth question. For the field in P3, which way does a small -1 microcoulomb charge placed at 0.4, 0 accelerate? So if you took a look at what we just do, right? I probably shouldn't have raised it, but that's that. So same, it's placed over here, right? This time we have the negative charge here. Which way does it accelerate? So you might be tempted to say that because what we do, right? Because of what we do, the vectors would push it this way, rightward, because both are pushing horizontal, outwards, and downward. But you have to be careful, right? The acceleration of a charge, let's write this down, acceleration of a charge, right, is always opposite to E. Okay, so whichever direction E is telling you you're going to go, your charge is going to go opposite to that. And of course, that's only when you have opposite charges. So you got to be a bit intuitive here. You can't, there's too many rules to memorize, right? Just think about it. This same negative charge, it's going to be attracted to both these protons, right? So it's going to be attracted that way. It's going to be attracted that way. And when we saw the electric field, it was saying it was going to be pushed that way and pushed this way. So we just flip this over here. Okay, so it's going to be pushed back and up. So that's only for the electron, right? It's going to do the opposite of, so I don't want to say electron, it's just opposite charges for these. So you have to be very careful here, right? Because it does get a bit tangly depending on what you have. For example, if you had a proton here, it would just accelerate along the field, right? Along the field, same, this downward direction here. But if you had, for example, an electron here, and then you had a proton here, then that would be a bit complicated, right? You'd accelerate both this way, and you'd be pushed back this way. So you'd have to find out which one of these is greater. Okay? I mean, that is just Coulomb's law. You know, you can just find that out using Coulomb's law, right? I showed you a bunch of problems like that in 6.1. You can look over those if you feel trouble with this, okay? This isn't the video for that. So now let's go over drawing electric fields, okay? There are 6 rules that you need to keep in mind. Lines start on positive charges and end on negative charges. So positive charges push outward, right? We know that. And negative charges pull inward. Okay? Arrows point away from plus into minus. So same thing, just 2 different ways. Density is your strength. So, for example, if I had this electron, right? And suppose it does some weird stuff, and then it has some vectors like that, some vectors like this, okay? Then that means over here, your field is stronger, okay? More dense is equal to more strength, because that makes sense, right? There's a lot of field lines there. So obviously they're going to coincide and give you a stronger push or pull, okay? A stronger field in that area. So there you go. More density is more strength. You want to keep those in mind. Density, 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 right? That's your code word for field strength. Field lines are never going to cross, okay? So no business like this stuff or crossing like that. That's just straight out wrong. They don't cross. Always straight lines. Straight lines as in not like, not that they're always just going to move straightward, because there are forces, they can move like that or like that, but it's just that they have to start at a straight line and they're never going to cross, okay? The number of lines is proportional to the charge magnitude. So if I said, so it's up to me to decide, okay? But if I said a 1 coulomb charge has 3 field lines, then a 2 coulomb charge would have 6. Okay? The more lines there are, the similarly the stronger your magnitude of charge. Okay, so it's proportional in a way. If you have 3 coulombs, then you're gonna have 9. And this is just something I made up. Okay, don't take this as a set rule. You can be given 1 coulomb is 5 lines. Then you'd have to decide 2 coulomb is 10 lines. Okay, just like that. And the lines meet a conductor surface at 90 degrees, which means your lines can't start off like that. Okay, they can't start off in a weird way like this. They have to start at a 90-degree angle. Okay, so even if you're going to curve, so first let me go over the regular possibilities. When you have a line here, this is going to meet your surface at 90 degrees. Okay, it's perpendicular to here. So even if I had a line here, same 90 degrees. Okay, I can't have lines that twist so fast like that. Okay, but I can have a line that goes like this. So this is still 90 degrees, but it still curves, right? But I have to meet my conductor, my electron or proton, at 90 degrees. It can still curve after that, but the meeting has to be 90 degrees. Okay? So, yeah, this is just a diagram to show you what it looks like. Inward and radial for electrons, radial and outward for protons. Okay? So, when you have multiple charges, things start to look a bit different. If you do these field lines by yourself, right? Just for proton, you'd say, all right, well, it goes like that, it goes like that, just lines outward, right? But the straight lines, like completely straight lines, only happen when that's the only charge. When you have multiple charges, they start to intersect. So over here, when you have an electron, same thing, it pulls inward, pulls inward, pulls inward, pulls inward. But then what about the middle? What's happening at the middle? So we know that the proton and electron are attracted to each other, right? So the proton is going to send an outward force, an outward pull like that, and the electron is going to receive it because lines go inward to the electron. They're going to connect in a circular shape like that. Okay? And then there's going to be one straight line between them and similar circular shapes. Number of circular shapes is up to you, but it shouldn't take too much, right? There should also be straight lines because they're not always going to connect. They're going to have their own things, right? But they're always, so even if this straight line here was to curve a bit and still end up here, it's not all the lines are going to curve. Some of the lines are just going to do their own thing, okay? And similarly, if you have a proton and a proton, we know those can't intersect, right? That would cause, well, a lot of catastrophe, really. You can't have two protons attracting each other. Even if you push them very close apart, a lot of stuff is going to happen that you probably don't want to know. So proton, same radial outward lines, right? And over here, instead of intersecting like they do here, because they're attracting each other and pulling on each other, here they're going to push each other away, okay? So usually this line would go straight like that. But then what would happen? It would intersect with this field line. We can't have intersections. So in the case of attraction, we just turn it into one line that represented attraction between both of them. But here we know we can't change it into attraction. So we have to represent it differently. We have to think of an asymptote, right? Think of like an asymptote. They approach each other, but they never really meet. They just repel each other. Okay? They push on each other, but then they just warp each other around. They go like that. And an interesting fact is at the center over here, you're gonna feel no force. It's called a null point. Okay? But we'll go over that in more detail in a bit when we go over gravitational fields. But that's what it looks like here. Similarly, right? If you had more lines, you would just draw like that. But other lines also do their thing, okay? It's not all the lines here, just lines in the vicinity. Okay. So what happens, however, when you have unequal charges? Okay. So if you had an electron, which is negative Q charge, and if you had a proton, which is positive 2Q charge, you remember what I told you about field lines, right? Electron, if the electrons was said to have 4 lines for just 1Q charge, right? Doesn't matter -1 or +1, it's just this number we care about. If it's 2Q, we just care about the magnitude, right? So a 2Q charge would ideally have twice as many lines. So this 2Q charge over here is going to emit twice as many lines, which you can see like this, right? So these 4 lines are shared by the 2Q and the Q, but this 2Q has 4 of its own lines because it has 8 lines, right? Because that's just how it is. If this electron here has 4 lines, the 2Q is going to have 8 lines because it's 2 times these lines, right? Magnitude directly corresponds with number of lines. Okay, so this is a bit extreme of a drawing actually. It wouldn't usually look like this, right? I would probably, if I was given 4 lines, I'd probably make 2 of them attractive lines like this. I'd probably give that electron 2 of its own lines, right? And then the rest of the lines, the protons, rest of the lines, same, I just give it its own lines. I would probably wouldn't make it as extreme as this looks. But that's just the case now, okay? All right. And always remember, right? These lines run to infinity and they don't intersect. So don't intersect these lines. Even over here, you might be very tempted to go, all right, maybe I should just angle them in one point. But these lines don't intersect, okay? Electric field lines just don't intersect, so you wouldn't do that. All right, so let's try some sketching problems here. Sketch the field of a single -3 microcoulomb charge. Which way do arrows point, and where is the field strongest? Okay, so a tad bit of a trick question here, right? But let's walk through it together. So -3 microcoulomb. The electron, -3 microcoulomb. And which way do arrows point, and where is the field strongest? So arrows are going to point radially inward, because that's just what happens to an electron, right? And the field is strongest closest to the charge, right? Because think about it, if you had another charge over here, then these two lines are pretty close to each other, right? This is the point at which they're the closest, actually. As you move on upward, this distance keeps increasing between them, right? So they're going to be the most dense near as close as possible to the charge, because they originate from the charge. So they're going to have the closest distance at the charge. So not that bad, but you could get tripped up on the where is the field the strongest. Okay. Sketch the dipole for 2 microcoulomb proton and a 2 microcoulomb neutron 0.4 meters apart. Mark where the field is strongest and its direction at the midpoint. Okay, so 2 microcoulomb here. And what do we know? This is a proton. So actually, I'm just going to write plus 2q. Okay. And then we have minus 2q. And they're both 0.4 meters apart. We need to mark where the field is strongest and its direction at the midpoint. So at the midpoint, right? Think of what would happen. At the midpoint, or before that actually, let's go over where the field is strongest. So if I was to draw just the field here without anything else, it probably looks something like this, right? Intersect here, intersect here, maybe another intersection, maybe another intersection, then same, its own things, same amount of lines, right? Because they have the same magnitude. And over here at the midpoint, so before that actually, where is the field the strongest? The field is the strongest in the gap between them, okay? So what I mean by that is in this tunnel, okay? In this entire region, it's the strongest. Over here, these lines are spread out, but when they're attracting, they're going closer and closer to each other, okay? So any charge is going to feel a lot of power in there. Charges like over here are not going to feel as much power as they're going to feel over here, because the lines are so close to each other. Then there's a lot of lines there. It's attraction, right? So they're going to feel it in that area. And at the midpoint, it's just going to be rightward, right? Because the proton is emitting rightward. It's emitting away from itself. And the electron is taking into itself, right? So either way, it's going rightward. Okay. So now let's look at a bit harder problems. We need to sketch the field of 2 3 microcoulomb charges. Okay. And mark the null point and explain why no field line passes through it. So the positive 3 microcoulomb charge. So we have it partially drawn, but we just have to draw the other part. Okay, so which is basically like we have to extend it, right? Let me just show what exactly is happening here. We'll probably add a few more lines here. Here. Sure. And then this is an imaginary asymptote. You definitely do not add this in an actual test. Okay, I'm just doing that to give myself an understanding of where I have to not draw. Okay. And then from there, the reason that over here there's a null point is because if you think about it, right? At that point, if hypothetically we had a proton emitting a field at that point, then radially outward, right? Over here, also radially outward. So what are they going to both do? They're both going to cancel, and there's going to be nothing there, a null point. So even if you placed a little electron right there, right, you would feel attracted to both of them, but it wouldn't move anywhere because the fields cancel over there. But why are there field lines still here, if you ask, right? Because it's pretty close. Any point that's equidistant from both of them, at the distance d, that's going to cancel out because they're both going to have the same field at that point. These asymptotes, they're, if I placed a charge here, right, even though it would be very close to this positive charge, it's still closer to this positive charge. So this positive charge will have the edge over it, and it's going to have it in its own field, its own domain. Okay, and that's why no field line passes through it, because it's null at that point, right? There's nothing there. So, I mean, I just explained it. I'm not going to write everything here. Okay, a 2 microcoulomb and a negative 1 microcoulomb charge sit 0.5 meters apart. How many lines leave the plus versus enter the minus, and where do the extras go? Okay, so twice as many lines, leave plus, then enter minus, right? And why is that? Because minus has 1 microcoulomb. So it's going to, suppose if it's only 4, it's going to take in 4 lines because electrons attract lines inward, right? And the proton, however, because it has 2 microcoulomb, it's going to emit 8 lines. So 4 lines will go to the electron, and other 4 lines will just do their own thing, okay? All right, sorry about that, whatever that was. And from that, you understand that they have to go like that, like that, like that, like that. And if you're going to follow the 4 example that I was talking about, you'd have to understand that there'd be lines that would probably go out like that as well, okay? And where do the extras go? The extras go in their own direction, right? They don't attract here because that would be too much attraction force. You can only have a certain amount of attraction because the electron itself can only take in a certain amount of lines. It can't take in more than that, right? Because it has a limited amount by the charge it's designated. If it has a larger magnitude, it can take in a larger amount of lines. But since it doesn't, it's going to be only able to take in a few lines. Okay? So the extras are just their own thing. They just go away and they make their own field, but a considerably weaker field. The field is strongest in here because it's so dense. And next video, I'll go over harder drawing problems for fields, okay? Because these were relatively easy. I want to show you what happens when there's 3 or more charges and how the fields will look in that scenario, okay? So stay tuned for that, and we'll also go over gravitational fields as well as the triboelectric series. So do stay tuned for those, and make sure to give a like and subscribe to continue on your physics journey and keep up with the latest content. Thank you for watching.